Now we talked about the concept of conservative field from class 11th, that is one. Okay, so the first concept was the concept of conservative field. Okay, field. Okay, that was number one. The second concept is that of the work energy theorem. Now, what does it say? Now, conservative field, we had seen three things, right? We had seen that W is independent of path. That is number one. The second was W is equal to 0 for closed loops. Third was Ux can be defined so that Fx is equal to minus du upon dx. U is the function of x. These three things we saw, and a direct fallout of that is that mechanical energy in a conservative field is conserved. Okay? So fallout of this is that the mechanical energy, this we have done in the class 11th video, so if you want to know it in greater detail or go into the proofs of it, you can go back and refer to that video. Okay, so mechanical energy is conserved. And what is mechanical energy? What is mechanical energy? Kinetic potential. There are two types of this, the Ke, the kinetic energy, and the potential energy. Okay, so this maybe this and potential energy. So the sum of it, the total, the kinetic plus potential is equal to a constant in a conservative field. Mechanical energy remains conserved. Fine. Now, if I so what does work energy theorem say? What does it say?
That the initial work done is the energy spent is always equal to the final work.
It says that whatever work you do gets stored into the system as a kinetic or a potential energy, right? Any work done gets stored into the system as a Ke or a Pe or both. Now it depends on you. Okay, it does not go waste. So in a gravitational field, you raise the brick by height h or x, you do a work mgx, and its potential energy goes up if you do it without accelerating. Okay, so all of your work, why do I put that restriction of not accelerating? I want all my work done to move into the potential energy, and that can be done only by restricting the kinetic energy. And what is the kinetic energy? Half mv square. So I have to restrict the v. So I have to keep my v infinitesimally small. You get the point? I have to keep my v infinitesimally small. That's why all my work done gets translated into potential energy.
Why not say keep V
if V is 0, how will it move from one place to another? After all, you have moved the brick from here to here. There is a displacement.
So it stops after some time, right?
Hmm?
After stopping it, the work done will be equal to the KE potential.
Try to understand what happens, why we do this. Even if you were accelerating that brake and then braking it, for example, I pick this pen and I put it here. So in some part of the journey I have accelerated, and in the other part I have decelerated. Then only that is possible, no? And this happens with so many things. Acceleration, deceleration has simultaneously occurred, and your control system, the body, exactly knows when to accelerate and when to decelerate. Understand? Do we understand that? So many things, say, so many things are built on your mobiles are built on such accelerometers. It detects that maybe if there is a stylus in it and you start moving without this stylus, it understands that you're moving away just by noting your acceleration, and it gives you a warning that you have left the stylus somewhere. Okay? Understand? So the energy that would have gone into the kinetic energy would have been returned to you while you were braking, but that becomes a bit complicated. So we do not want to go into that complication. We are saying that all the work we are simply not letting move it into the domain of the kinetic energy. So whatever is the work done remains in the domain of potential energy. And when you were trying to move all the work into the kinetic energy, you did not want it to move into the domain of potential energy, and for that what you did, you took a horizontal surface. If I took a surface like this, here the potential, maybe whatever is the work done, that is getting translated into a potential as well as kinetic. So we had done it for a horizontal surface. Okay, understand? So right now I am talking about the potential energy. Okay, I am talking solely about the potential energy, and I'll try to see if there is a charge plus q here. Okay, and in this direction from this charge. Okay, say a charge small q is taken from point R to P. Okay,
Positive or negative?
this is also positive. This is also a positive charge. Okay, this is a smaller charge. Okay, this is a test charge kind of thing. This is the source charge. Okay, we have a plus q charge fixed at some point, and move a charge q from a point R to P. Okay, without accelerating, the charge q, without accelerating q. Fine. Let the work done in doing so be designated WRP. Work done in moving from R to P. Okay. So what will it be? We will soon go into the nitty-gritties of that, But let us try to understand. As I start coming closer to this, okay, as I start coming closer to the charge plus q, the plus q, what happens? What happens? Both are positive, so there is a force of repulsion, correct? And I know the exact value of that by Coulomb's law. Is it not? Is it not? So what happens? Say if this distance is r, if this distance is r, then my force is actually dependent on that r. Understand that? That force is dependent on that r. So we are encountering a variable force whose magnitude depends on the magnitude of r. Do we get that? Now there is a trouble. Force is force multiplied by displacement. Okay? Force multiplied by displacement, and that is true when f is a constant. So what do? I move it by such a small distance. I'm showing it here as a big distance. This is a very large distance. But you should understand that this is otherwise magnitude wise very small. So some dr distance. Okay? And I have applied a force in this direction. Okay? I have applied a force in this direction. This is my F external. Why do I call so? This is the external force that is applied on charge small q so as to just overcome the force due to q on this. You understand, the force is a repulsive force. Here on this, due to plus q, the force that is applied is a repulsive force. Okay? This is the system force. F system. Now what am I doing? I am trying to move the charge in a direction opposite to the force that it is experiencing. Do we get that? So I'll have to apply a force of my own. If I leave it here, I do not do anything, it will fly off rightward, right? It will go to the right. Now I do not want that. I have to bring it closer. So I have to apply a force. Now what is the magnitude of that force? That force should be such that it is just first of all in the opposite direction and then infinitesimally greater than the F system. Do you get that? This is the system force. It has to be just slightly greater than F system, infinitesimally. Okay? So what happens? What is WRP? So with this force, I am applying some external force. I am applying some external force. So WRP is equal to dWRP. Some infinitesimal amount of work done is equal to F external, which is a function of R dot dr. Do we get that? It is F external, which is a function of R dot dr. And if I want the whole work, I should be integrating from R to P the above expression. So this is the total work done in moving from R to P. We'll soon calculate it, don't worry. Don't worry. We'll calculate it, we'll designate it something, we'll do a whole lot of things. Don't worry about that. But this is how we'll proceed. Okay? And you should understand one thing, that F system which is marked in red. So let me write it in red. That F system, is negative of, or I should say F external is negative of. Both are the same thing. F external is equal to F external, which is a vector, is opposite to F system, and since it is just infinitesimally greater, this is negative of that, right? It is just infinitesimally greater, so I write them to be almost equal. Okay? Though there is an equality sign, there should be a slight approximation because it is not exactly equal. If it is exactly equal, then the unbalanced force will be 0, and the system will not accelerate at all. Fine. It will not accelerate. So I'm using the equality sign.
It will be at rest.
It will be at rest. It will never move. It will never budge. Okay. Now what happens? So I can write this as F external is minus F system. So WRP can also be written as minus F system dot dr r to p. Do we get that? So this is the work done. Is it not? This is the work done. R to P. Fine. Fine. This is the work done. Now we come to what we were discussing, the work energy theorem. I have done some work. I have not let it move into the domain of kinetic energy. So it is all your potential energy. So what does it mean? It means that if so I say if the potential energy at R is UR and at P is UP, then what happens? Whatever is the potential energy at R, UR, plus the work that you do in moving from R to P, correct? This is your work done, becomes UP. Get that? Do we get that? So WRP is nothing but UP minus UR. Okay. Okay. So do we understand that? Do we understand this? And the second is the fallout of that, but nevertheless important. In defining the potential energy. Correct? So how do you define the potential energy difference between the 2 points? It is equal to the work done in getting an arbitrary charge from one point to another. No? So that's how it is defined. The potential energy difference between 2 points is defined as